Los Alamos, 1943. Two physicists stand at adjacent blackboards. The problem? Calculate the uranium diffusion rate for the atomic bomb. Hans Bethe, IQ measured at 170, head of the theoretical division, begins filling his board with differential equations. 6 pages of mathematics. Richard Feynman, IQ tested at 125, pulls out a notebook and starts drawing pictures. 40 minutes later, Feynman has the answer. Bethe is still calculating. Bethe walks over, studies Feynman's notebook, and says something that would echo through physics for decades. That's not mathematics. He stops. Because what he's looking at shouldn't work. It violates every principle of how high intelligence problem solving is supposed to function. Yet the answer is correct. More than correct, it's elegant. And the method Feynman used, documented across 47 notebooks from MIT to his death, would let him consistently beat physicists with IQs 50 points higher. By the end, you'll know the exact system. But first, you need to see why everything you've been told about intelligence is measuring the wrong thing entirely. The education system built a monument to IQ. Schools track students by test scores. Corporations use SAT and GRE as intelligence proxies. Mensa memberships become LinkedIn credentials. Graduate programs reject candidates who score below cutoffs. Tech companies design algorithm interviews that correlate with pattern recognition speed. The underlying assumption, higher IQ equals better problem solving. Then the data arrives. Feynman's IQ of 125 sits barely above average for physicists at Los Alamos, where the mean was 150. His sister Joan, also a physicist, scored higher. 5 of his Princeton colleagues had documented IQs above 160. John von Neumann, who Feynman worked alongside, tested at 190, the highest recorded at the Institute for Advanced Study. Yet when the Nobel Committee awarded the 1965 Physics Prize, they cited Feynman's path integral formulation, not von Neumann's, not the 180 IQ mathematicians who worked the same problems. Feynman's. Something was fundamentally broken about the measurement system. And this changes everything about how you approach learning, interviews, and career advancement. IQ tests measure one cognitive skill, while breakthroughs require a completely different one. Schools don't teach Feynman's method because it exposes an uncomfortable truth. What standardized tests reward has almost nothing to do with what creates original thinking. The proof comes from documented competitions where Feynman and high IQ physicists attacked identical problems. Same equations, same constraints, opposite approaches, and in every case, the pattern reveals why you've been optimizing for the wrong metric your entire academic life. This is why you freeze in technical interviews despite knowing the material. You memorized algorithms. The interviewer changes one constraint. Your mental model collapses. This is why credentials don't guarantee problem-solving ability. The PhD who aced qualifying exams can't generate novel research questions. This is why high IQ people plateau while others break through. Pattern recognition, speed hits a ceiling. Pattern creation ability doesn't. Feynman optimized for the second. And the method is documented in sources anyone can access. Surely you're joking, Mr. Feynman. His Nobel lecture, the Feynman lectures on physics, the Rogers Commission testimony. But here's what doesn't make sense. If the method is published, why doesn't everyone use it? Because it contradicts the industrial model of education. Schools need standardization. Feynman's method requires customization. Tests need scalability. Feynman's approach demands depth. The system needs you to believe intelligence is fixed, because that justifies sorting students into tracks. Feynman proved intelligence is a method because that would require completely rebuilding how institutions operate. To understand how a 125 IQ physicist consistently outsmarted the highest tested minds of his generation, we need to see what actually happened when they faced the same problem. Los Alamos, 1943. The Manhattan Project had hit a calculation bottleneck, and what Feynman did next wouldn't just solve the uranium problem. It would expose why everything about IQ testing is backward. The theoretical division needed diffusion calculations. Fast. Bethe assigned the problem to his team, physicists with credentials from Princeton, Cambridge, MIT. They approached it the way high IQ problem solvers are trained: retrieve the relevant equations from memory, apply the standard mathematical framework, solve through symbolic manipulation. Beth, who could multiply 4-digit numbers in his head, used this method. It worked. It just took 6 hours. Feynman looked at the same problem and made a decision that defied conventional intelligence. He refused to use the standard approach. As documented in Surely You're Joking, Feynman didn't start with equations. He started with pictures. He drew physical representations of uranium atoms diffusing through barriers. He visualized the motion. Then, and this is the detail that changes everything, he invented his own mathematical notation to describe what he was seeing. Not borrowed, invented. The calculation took 40 minutes. When Bethe saw the method, he initially thought Feynman had made a mistake. The notation looked wrong. It didn't follow Schrödinger's equation format, but the answer matched. Then Bethe tested it on a harder problem. Feynman's method was faster again. What looked like a trick was actually a system, and the system exposed something the IQ test completely missed. IQ tests measure how quickly you recognize existing patterns. Can you see that 2, 4, 8, 16 follows a doubling pattern? Can you identify which shape completes the sequence? Speed of pattern recognition. Feynman's method optimized for pattern creation. When you face a problem with no existing template, pattern recognition fails. You need the ability to build a new framework from scratch. This wasn't about being smarter. It was about cognitive architecture. High IQ physicists had better RAM, faster memory retrieval, quicker symbolic processing. Feynman had better compiler, the ability to reconstruct understanding from first principles every single time. In stable domains where templates exist, RAM wins. In novel domains where you're solving unprecedented problems, the compiler dominates. The Manhattan Project was entirely novel. No one had built an atomic bomb before. Existing physics templates didn't fully apply. Feynman's method worked because it didn't depend on inherited models. But here's where it gets deeper. Because this principle, reconstruction over memorization, applies directly to why you fail technical interviews in 2024. When you're preparing for system design questions, you memorize patterns. Load balancer goes here, cache goes there, database. Sharding uses consistent hashing. Then the interviewer changes one requirement. Your memorized template breaks. You freeze. Feynman's approach. Don't memorize the architecture. Rebuild it from scratch every time based on the constraints. Understand why the load balancer exists, what problem it solves, what happens if you remove it. When the constraint changes, your understanding flexes. The template memorizer fails. The first principles rebuilder adapts. This is the competitive advantage IQ tests don't measure. And it's entirely learnable because it's not about intelligence. It's about method. But the Los Alamos calculation was just the beginning, because Feynman would face a competition that exposed the IQ myth even more dramatically. Princeton, 1941. Feynman is a graduate student. His advisor, John Wheeler, gives him a problem in quantum mechanics. Develop a new formulation of quantum electrodynamics. The existing approach, based on Schrödinger's wave equation, has mathematical inconsistencies. Every physicist in the world is using Schrödinger's framework, including Julian Schwinger at Harvard, IQ estimated above 160, known for solving quantum problems faster than anyone in the field. Wheeler tells Feynman and Schwinger they're both working on the same problem, a race. Schwinger takes the conventional path, master Schrödinger's equations, identify the inconsistencies, patch them with more advanced mathematics. This is what high IQ training optimizes for. Take the existing expert model and push it further. Feynman makes a decision that seems insane. As documented in his 1965 Nobel lecture, he ignores Schrödinger entirely. He goes back to Newton, classical mechanics, particles following paths. Then he asks, what if I could describe quantum mechanics using only paths, no waves? This violates everything. Quantum mechanics is wave mechanics. That's the foundation. Feynman doesn't care. He builds a completely new mathematical framework from scratch. Path, integrals, the idea. Instead of describing one wave function, describe all possible paths a particle could take and sum them. It takes him 3 years. Schwinger finishes first. 1948. His formulation is published. Mathematically rigorous. Complex. Only experts can follow it. Feynman finishes second. 1949. His formulation is published. It looks nothing like Schwinger's. The physics community is confused. Two completely different mathematical frameworks. Both solve the same problems. Both predict identical experimental results. Then something happened that contradicts everything about how IQ is supposed to work. Schwinger's method, for all its mathematical sophistication, became a dead end. Physicists could use it to calculate results, but they couldn't intuitively understand what was happening. The math was too abstract. Feynman's method became the foundation of modern physics. Why? Because his path-integral approach could be visualized. Students could draw Feynman diagrams, pictures representing particle interactions. You didn't need an IQ of 160 to use them. You needed to understand the principle. By the 1960s, every physics student learned Feynman diagrams. Almost no one learned Schwinger's formulation. The Nobel Committee awarded the prize to both, but Feynman's method revolutionized the field. Schwinger's didn't. What's the difference? Schwinger optimized for mathematical rigor, the kind of abstract symbolic manipulation that IQ tests measure. Feynman optimized for understanding from zero, the ability to explain complex phenomena using simple building blocks. As Feynman stated in his Nobel lecture, "I had a scheme which I still use today when somebody is explaining something that I'm trying to understand. I keep making up examples, not memorizing their examples, making up new ones." This is the second principle. First principles beat inherited models. When you inherit an expert's model, you gain speed but lose flexibility. When you build from first principles, you gain understanding that transfers to new domains. High IQ training teaches you to master existing frameworks faster. Feynman's method teaches you to create new frameworks when existing ones fail. And this principle applies directly to why credentials don't guarantee innovation in 2024. Companies hire the MIT PhD with perfect GRE scores. 6 months later, they wonder why the hire can't generate new product ideas. Because the PhD spent years mastering existing frameworks. Optimization, not creation. Compare that to the self-taught engineer who rebuilt every technology stack from scratch. Slower initially. But when the company needs to solve a novel problem, something no existing framework handles, the self-taught engineer invents the solution. The credentialed hire searches for a template. This is the difference between Schwinger and Feynman, both brilliant. One optimized for playing the existing game better, the other optimized for inventing new games. IQ tests measure the first. Breakthroughs require the second. But we still haven't seen the most extreme example. Because there was one moment where Feynman's method didn't just beat high IQ physicists. It embarrassed an entire institution of credentialed experts in front of the world. January 28, 1986. The Space Shuttle Challenger explodes. 7 astronauts dead. NASA convenes the Rogers Commission to investigate. The commission includes Neil Armstrong, test pilots, aerospace engineers, the highest credentialed minds in their fields. They begin the way institutions always do: request reports, review documentation, hold formal hearings. NASA engineers present data, charts, statistical models, probability calculations showing the O-ring seals were safe. The engineers have PhDs from MIT, Caltech, Stanford. Their analysis follows rigorous methodology. Richard Feynman, now 67, is appointed to the commission. He has no aerospace engineering credentials. He's a theoretical physicist. Particle. Interactions, not rocket engines. The other commission members expect him to defer to the experts. Instead, Feynman makes a decision that exposes the entire IQ credential system. He ignores the reports. As documented in What Do You Care What Other People Think? Feynman goes to the NASA hangars and talks to the actual engineers who built the O-rings, not the managers, not the PhDs presenting to the commission, the mechanics. He asks basic questions. What temperature was it the night before launch? How do rubber O-rings behave in cold? The mechanics tell him something the official reports didn't. The O-rings become brittle in freezing temperatures. Feynman gets ice water and a piece of O-ring material. During the televised commission hearing, while NASA engineers are presenting complex statistical models, Feynman drops the O-ring in ice water. He pulls it out, squeezes it. It doesn't bounce back. He holds it up to the camera and says, "I discovered that when you undo the clamp, the rubber doesn't spring back. It stays the same dimension. In other words, for a few seconds at least, there is no resilience in this particular material when it is at a temperature of 32 degrees. The room goes silent. Months of credentialed analysis. Thousands of pages of reports. Feynman just destroyed it with ice water and a piece of rubber. The NASA engineers in the room know exactly what happened. They'd been reporting O-ring concerns for years, but the official reports filtered through management layers. The statistical models abstracted away the physical reality. Feynman bypassed the entire system. He went to direct observation. This is the third principle. Direct observation beats abstraction. High IQ training teaches you to trust models, trust data, trust expert reports. Feynman's method teaches you to test reality directly. When the model contradicts the experiment, the model is wrong. Always. As Feynman wrote in his appendix to the Rogers Commission report, for a successful technology, reality must take precedence over public relations, for nature cannot be fooled. Not might take precedence, must. This wasn't about Feynman being smarter than NASA's PhDs. It was about method. They optimized for credential-approved analysis. He optimized for physical truth. They abstracted. He observed. They trusted institutional processes. He trusted experiments. And the method worked because reality doesn't care about IQ scores. But here's what most people miss. This principle applies to every domain in 2024. You're evaluating a startup's pitch deck. Beautiful slides, impressive projections. The founder has an MBA from Stanford, IQ probably 140 plus. Everything looks credentialed and rigorous. Feynman's method, ignore the deck. Talk to their actual users. Ask basic questions. Does the product work? Do people pay for it? What happens if you remove one feature? The credential worship approach trusts the abstraction, the pitch deck, the financial model, the founders, pedigree. The Feynman approach tests reality directly. Which method catches fraud? Which method identifies actually valuable companies? The direct observation wins every time because markets like nature cannot be fooled by credentials. But there's one more competition that reveals the deepest layer of why IQ is a trap. And this one takes place in a classroom, Caltech, 1961. Richard Feynman starts teaching undergraduate physics. His colleagues in the department are among the highest IQ physicists in the world, many with measured IQs above 160. They've been teaching quantum mechanics for years using the standard approach. Start with a mathematical formalism, derive the wave equation, show applications. Students struggle. Dropout rates are high. The professors blame the students. They're not smart enough for quantum mechanics. Feynman is assigned the introductory course. He makes a decision that horrifies his high IQ colleagues. He refuses to use the standard curriculum. Instead, as documented in the introduction to the Feynman Lectures on Physics, he starts from zero. Not zero mathematical knowledge, zero assumptions about what students should already know. He asks, if I had to explain quantum mechanics to someone who never took physics, what would I say? His colleagues think this is impossible. Quantum mechanics requires advanced math. You can't teach it to beginners. Feynman proceeds to teach quantum mechanics to freshmen, using minimal math. The lectures are recorded, published. They become the most influential physics textbook of the 20th century. 60 years later, they're still in print, still used, still considered the clearest explanation of quantum mechanics ever written. What did Feynman do that the high IQ professors couldn't? The high IQ approach. Assume students have prerequisites, build on existing knowledge, cover material efficiently. This works for students who already understand. It fails for everyone else. Feynman's approach. Assume nothing. Build understanding from first principles. Prioritize clarity over coverage. As Feynman explained in the lecture introduction, I learned very early the difference between knowing the name of something and knowing something. The high IQ professors taught names. Schrödinger equation, wave function, uncertainty principle. Students memorized the names, passed tests, didn't understand. Feynman taught the concepts. He used examples, thought experiments, physical intuition. Students understood, could apply to new problems, could teach others. This is the fourth principle. Understanding beats performance. High IQ training optimizes for performance on tests. Quick recall, pattern matching, symbolic manipulation. Feynman's method optimizes for deep understanding, the ability to explain, to apply, to extend. Performance is faster initially. Understanding is more powerful long-term. Performance creates employees who can execute known tasks. Understanding creates people who can solve unknown problems. The difference becomes extreme in fields where the problems keep changing, like technology in 2024. You're learning a new programming framework, the high IQ approach. Memorize the API, copy Stack Overflow solutions, pass the certification exam. Fast, efficient. Then the framework updates. Your knowledge is obsolete. Feynman's approach. Understand why the framework exists, what problem it solves, how it works internally. Slower initially, but when the framework updates, you understand the changes. When you switch frameworks, the principles transfer. When you need to build something the framework doesn't support, you can extend it. This is why self-taught developers often outperform computer science PhDs in rapidly evolving domains. The PhD optimized for credential-approved knowledge. The self-taught developer optimized for first principles understanding. The domain changed too fast for credentials to keep up. Understanding adapted. Performance couldn't. When you combine all four principles, reconstruction over memorization, first principles over inherited models, direct observation over abstraction, understanding over performance, you get something IQ tests fundamentally don't measure: the ability to build knowledge from zero in any domain. This is why Feynman won the Nobel Prize, while physicists with higher IQs faded into footnotes. This is why he could explain quantum mechanics to undergraduates when 180 IQ professors couldn't. This is why he solved the Challenger disaster when NASA's credentialed engineers missed it. IQ measures pattern recognition speed. Feynman optimized for pattern creation ability. The first makes you good at answering existing questions. The second makes you capable of asking new ones. Schools test pattern recognition because it's standardizable. You can grade it, rank students, sort them into tracks. The world rewards pattern creation because it's what actually produces breakthroughs, new physics, new companies, new solutions to problems no one has solved. The system can't teach Feynman's method because it would expose that credentials and IQ scores are measuring the wrong thing entirely. As Feynman stated in his Caltech lectures, the first principle is that you must not fool yourself, and you are the easiest person to fool. Every time an institution told you that you weren't smart enough for the program, the job, the project, what they actually measured was your ability to perform on their pattern recognition test. Not your ability to create new patterns. Not your ability to build understanding from scratch. Not your ability to observe reality directly and trust what you see over what experts claim. Those abilities are what Feynman used, and they're entirely learnable. Richard Feynman died in 1988. His IQ of 125 never changed, but the method he built, documented in 47 notebooks, published lectures, commissioned testimonies, and biographical accounts, outlasted every genius who tested. Higher, because intelligence isn't a fixed number, it's a system, and systems can be learned, copied, and improved by anyone willing to abandon the credential game. The competitive advantage you've been searching for isn't a higher IQ, it's a different method. The question is whether you'll keep optimizing for pattern recognition speed or start building pattern creation ability. One gets you credentials, the other gets you breakthroughs. Feynman proved which one actually matters. But this method was just one piece of how Feynman operated, because he used another technique for learning complex material faster than people who spent 10 times more time. And what he discovered about memory contradicts everything schools teach about studying. Most people get it completely backward.